Good morning, everyone. So thanks for inviting me here. And today, I realize that I'm standing between you and lunch, so I try to be fast. So my topic here today is exploring on-chain data analytics. Now, first of all, my background has always been with AI and the data for the past 25 years, and I graduated from UIUC majoring in with a topic on graph learning and graph mining. The reason why I became interested in on-chain data analytics for the recent years is because I realized that blockchain data is actually the best data for research community, right? If I recall, like in my PhD days, the data set I've been used the most is the DBLP data. And we've churned out many papers on that. The reason why the research community likes DBLP data so much is not because it's great or it's so rich. The only reason is because it's actually free, available, and actually everybody can use it, everybody can cite it. But if you consider blockchain data, right, it is actually even better, right? We have all the publicly available free data that, and it's evolving. And you can potentially do cross-domain correlation between, for example, blockchain data and the Twitter data and the many other social network data. So you can sort of like build this cross-platform data analysis and correlate it even with price, token price. So that is why we think that it is high time that we try to introduce all these on-chain data analytics to the greater machine learning AI community. So from a couple years back, I was trying to introduce blockchain data to, for example, the KDD community, the SIGMOD community, right? So that people start to look at this data from the analytic perspective. And I'd like to share a bunch of stuff that we're currently working together with my PhD student, trying to examine on-chain crypto asset from a number of different perspectives. Now we have, of course, lots of things to study for on-chain data analytics, right? So what will be the central theme? So we sort of come up thinking about that there are a couple domains or pillars that we think are important for on-chain crypto assets, right? First of all, decentralization, of course, because the core idea and the underlying principle for almost all the crypto project is decentralized control, right? So, but it is interesting that, for example, take Bitcoin as example, right? From the consensus design, of course, the ideal is that in the future, it will be fully decentralized. But after 15, 16 years of development, how decentralized it is from the asset perspective, right? Very few people have been looking at the problem is, how decentralized is Bitcoin now as an asset, really, right? I mean, not just from a theoretical perspective. So, and this applies to other tokens as well. And we can potentially look at, for example, all these wealth distribution, correlation to market, causality problems from the decentralized perspective. Now, second, asset needs to flow, right? Because liquidity is one of the key notions for asset. So that is why we are also interested in the fluidity of the token. And there we can look at, for example, token flow, flow structure, event-driven flow, all these topics. And then we have all the rich flow-based graph technique, a graph algorithm to help us. And lots of things that we've been using in the graph learning theory can help us here. Thirdly, connectivity. Because when you view the entity, whether it's an address or whether it's transaction, and you build network on top of that, there are lots of connectivity issues we can examine. For example, we can look at address level, entity level, community level. And I have many years of research experience on social network. And not surprisingly, many of the social media discovery network, community detection, link prediction, right, pattern mining, all these interesting algorithms can naturally be borrowed into this connectivity research. And the last but not least, the regularity, because if you look at the graph from a much larger granularity, right, there are lots of larger pattern you can observe. For example, temporal patterns, structures, price patterns, how the community evolves, sorts of things. And knowledge graph can also be extracted from the regularity. So that's why we think if we have this higher level framework, right, all these four central themes, and then we can branch out all to the smaller topics and And for the past few years, my student and I have been looking at some of these topics. So today, because interest time, I can only share a few of them. So I'd like to first introduce our research based on the network. Basically, is from the network modeling of the crypto asset to the network profiling, as well as the network-based detection. Luckily, there are lots of the reason machine learning, the AI technology, including graph learning, representation, neural network can be applied to this. And eventually, we can also leverage, for example, nowadays a large language model, right? Try to explain and interpret the trader's intention or even the hacker's illicit address intention from this transaction network. So to start with, right, I mean, we did some interesting work on the Bitcoin asset decentralization from several perspectives. One perspective is to look at the mining distribution, right? From the point where, from the miner perspective. So when miners get the Bitcoin from the Coinbase, how decentralized it is from that perspective. So here, for example, the left-hand side, you're seeing the green line is the entropy of the uniform distribution, right? Supposed to be the most decentralized curve. And then the real distribution is shown in the blue. And the divergence between the two curves essentially can be used to measure the deviation from the most decentralized degree. And that is which is actually shown on the right-hand side. So from that, you can see that there is a bunch of drop in terms of decentralization over the years. And at a certain point, for example, near 2016, where we had the second halving day, there is a certain sharp increase in terms of decentralization. Probably mainly because of the drop of the profit. Some of the miners temporarily exit the market. And you can also look at asset distribution, right, from the static distribution perspective. Look at the proportion of the top, for example, 100, 200, 500 owners, Bitcoin addresses versus the entire asset. And then from the curve, it's interesting to observe that over the life cycle, it's easy to see that we have three phases of the asset distribution, right? For example, in phase one, there is a monotonous downward trend as the participation of nodes grow. And then at the second stage, which is roughly between, for example, 2010 to 2011, there is a sharp decrease in decentralization, right? This is probably because of some larger mining pools start to appear, and the people realize, wow, actually, Bitcoin can be an interesting asset. And then over the last, I would say, 10 or 12 years, you start to see a slow but steady increasing in terms of decentralization. Okay, and now it roughly stables at 0.4%. And then we can also look at the dynamic decentralization. Basically, is how often the top 500, 200, or 100 nodes actually changes position. So we use the typical and classic HHI in financial industry to measure the dynamic asset situation. And as you can see here is that there is actually a certain number of interesting points in history for the decentralizing degree based on HHI, and they all correspond to certain event in the Bitcoin life history. And then let's move on to fluidity. Right? How can we use the analysis of asset flow to, for example, detect illicit address early? And the early detection of fraud and early detection of illicit address has always been the central theme for crypto data analysis, because obviously people want to catch and identify or even monitor these illicit address from the right beginning. So for this problem, ideally we want early detection. We want it to be versatile. At the same time, we want it to be free from shadow event. And what are the popular current methods for now? Some of them based on visualization. For example, you can see here, right? People try to visualize those scattered centers, hierarchical transactions, long chain, self loops, and certain. There was another school of method tried to based on tracking analysis, right? That is leveraging more on off-chain information, but then you're going to actually to form these temporal paths to be tracked. Machine learning, right, from 10 years ago when it's become apparent that it's also going to be effective for this type of analysis, But for machine learning to be applied to this domain, you need to basically extract very, very effective features, as we know, right? There are all this nice feature engineering stuff. So you can look at all these different, basically address features, temporal features, centrality features, even motif features, right, for example. Graph neural network, right? The reason surge in the graph neural network, of course, is no exception. People try to leverage that for the crypto asset analysis. But unfortunately, one of the problems with this method is that actually the sophisticated method will rely on rich data, input data. But for example, for the graph neural network, for early stage, you won't be able to actually find a lot of data in terms of the transaction, right? Because it's understandable. Illicit actors just try to keep a low profile at the early stage when they are trying to do bad things. So you won't be able to observe a lot of, for example, chains, a lot of transactions in the early stage. And that is actually something very bad for these graph neural network data. Now, on the other hand, there are also a lot of, as we know, right, there is a shadow account use a lot of repeating chain actions, try to hide their intention and so on. And that is why we start to think about, can we create a network not just based on address, right? If you just based on address, then you won't have a lot of address information to be applied as an input for neural network. But what about we use transaction as node, right? We create transaction-based network. So here you see two graphs. On the right-hand side, if we use address as a transaction graph, even for 6 days for a Ponzi scheme address, the graph looks very sparse. And this type of data, it won't be very useful for a neural network algorithm because this input data is basically too limited. On the right-hand side, if we use transaction, right, as the node, we create asset transaction path and network. Then for a Ponzi scheme, even in just 1 hour, the network is much richer than the network in 6 days. So that is why we start to develop what we call asset transfer path based on all these crypto transactions. And here is an example with Bitcoin UTXO format. And we try to build what we call backward transfer path as well as forward transfer path. The idea is we try to capture the main asset flow out of this transaction graph. So once we have this backward asset path and a forward asset transfer path, we can create further what we call this backward path graph and the forward path graph out of these paths. The idea is that if the backward asset transfer path originates from one common node, then that represents what we call a diverging pattern. And if we can also use if there's some forward asset transfer path, they share one common destination, then this is a convergent path. Then we create a high-level graph that we can do all sorts of interesting clustering and the dense cluster detection algorithms on that. That will help us to identify the real source and destination of the asset flow. Then, of course, we build something we call Evolved Path Tracer using these graph encoders and the LSTM model, right? I will skip the details now. And the experiment demonstrates that not only that our algorithm will be effective in early detection, but also the ablation study shows that, yes, indeed, you will have to incorporate both paths in order for them to be the most useful. What's more interesting is that can we actually find out what's the underlying intention of these illicit address and malicious users? It turns out that we can leverage some intention monitor ideas from e-commerce study, right? For e-commerce, oftentimes if you want to find out what are underlying intention of people's browsing behavior, their purchase behavior, right? For example, here, if I see a trace of people's action, I can figure out, oh, maybe they are actually, for example, preparing for a travel or preparing for a marriage. But can we do the same thing for the crypto data, right? If we observe a number of transactions, can we find out what's the underlying intention? So the challenge is that if you see from this graph that there are actually no naturally defined, so-called actions, right? It's not like a click of a button or click on a link. So our first challenge is we need to somehow, first of all, find out feature and even build these segment sequence, okay? And then from the segment sequences, we then can able to finally build these different segments. Okay, in the interest of time, I will just move on faster. So basically, we can use all these path technique to do the prediction with survival analysis. So from the feature encoder to segment encoder to status encoder, we can basically do early prediction. And here is a case study. Remember back in 2019, there is a 7,000 Bitcoin stolen from Binance. And I quote here that it was unfortunate that we were not able to block the withdrawal before it was executed. So if we can detect the malicious illicit address earlier, there might be chances we can prevent the funds being transferred. So this is a case study. So we basically focus on this address, which initially got 567 BTC worth of asset, and then we try to use our model to analyze, and it turns out that using the model, by the 9th hour, if you look at this survival probability, by the 9th hour, we can 100% detect that this is already an illicit behavior, an illicit address. And then by tracing the decision tree from the root to the leaf, we can spell out the labels on the path, and this will help us to actually explain what is the underlying intention of the hacker, right? For example, here you see that what happens is that the hacker received a bunch of BTCs with a number of repeating actions, and at the 13th hour, it received a tiny amount of BTC before it transferred all the BTC out the 21st hour. And here we decode all these actions with our status. And you can even use nowadays large language model, for example, and ChatGPT to explain. When we pass our model and the data into ChatGPT, this is what ChatGPT gives out. It actually explains quite accurately what's happening, right, based on the intention and action of the malicious hacker. Okay, my time's up, and I want to conclude is that I think there is a very, very open area for on-chain data analytics for the whole machine learning and data mining community. And I don't know how many of you guys here are in this domain, but I think this is going to be a very good domain to research. So we're currently trying to build a global data platform for researchers around the world, especially in machine learning and AI, try to leverage crypto data for the analysis, because they may not understand the block structure, they may not understand how blockchain works, but they can look at the data once the data has been prepared partially for their usage. Okay, thank you so much.